Good evening. I'm Hussain, former professor, Department of Chemistry, University of Dhaka. We were arranging lecture on AS and A-level chemistry, a lecture series, and this is 41st lecture on reaction kinetics. Well, we have been talking about reaction kinetics, and which we named as reaction kinetics 1. And that is the reaction kinetics syllabus for AS level chemistry. But in A level chemistry, we continue with more quantitative data on reaction kinetics and how we measure, etc. So defining rate of reaction, what you do, that either a decrease in concentration of a particular reactant or an increase in concentration of a particular product over a period of time. That is what is rate of reaction, which I wrote here. Okay, we have to remember that we must be careful about the unit when we discuss the rate of reaction. The unit specifically, very carefully, we have to note it down. We know the concentration units are expressed in mole per cubic decimeter. Units for time are usually expressed in seconds. And then rate of reaction units are normally mole per cubic decimeter per second. Well, for very slow reaction, we may express the time as per minute or even per hour. We showed in earlier lecture, this is in 23rd lecture, how we use tangent of it to the curve and the shape of curves which obtain give us about the reaction mechanism also. But we will discuss in next few lectures in details about this. Here, what we are doing, we are showing reaction kinetics in a very simple language. If we say what is reaction kinetics, we will say the study of rates of chemical changes. That is what is reaction kinetics. We have been seeing that we use valence chemical equation to show what the reactant in the product and how we balance the reaction. That's what we discussed earlier, and we have been discussing this in many places about it. But this balanced reaction does not say anything about how fast the reaction will be or how we measure the rate of reaction using balanced reaction. Therefore, we have to do it, the amount of reaction products change during any chemical reaction. That is what is rate of reaction, and we call products form as reactant disappears. That means when the reactant disappears, we see that products are forming. The rate at which these changes happen give a measure of the rate of reaction. Well, several factors influences the rate of chemical changes. For example, concentration of reactants, surface area of solids, the temperature, reaction mixture, and the presence of catalyst. We learn much more about reactions by studying these effects quantitatively. Well, the first step we have to do, what we do, that we measure some component and then graphically represent it to see the rate of reactions. For example, if we take the experiment and plot it, the concentration against time in a graph, the gradient we get of the graph, we say that by this we measure the rate of reaction at that time. Let's see about this. This is a product, and we are looking product against time, and then we see that a graph is like this, and then we draw tangent on it, and by that tangent, we get the slope, that is gradient, rated at any time. This time, this is a tangent issue, and then we can see the rate of reaction for this product. Similarly, if we draw a graph with the reactant against time, we can find out the rate of reaction at a particular time by drawing a tangent at this one. That is what we call a concentration time graph, separating the reactant, and concentration time graph, the formation of the product. That's what we say in languages. Okay, what are the methods that we have to take into consideration for measuring this reaction rate? Well, we do have very many different methods. For example, let's say this is what is a figure in which we are showing that we take some magnesium turnings and add dilute hydrochloric acid, and then we draw the gas coming out from it. That's hydrogen coming out. We have we have a gas syringe and we measure the volume of the gas. That is one way. Another, we have we are doing a reaction here, reaction mixture containing acid, and then starting the reaction and taking time to time reaction mixture from here by a pipette and cooling it in ice cold water, and then titrating it against a standard solution of alkali, and we find the results. And we plot that concentration of the product against time. This is another way. And then we can use calorimeter, you see, calorimeter, and follow the reaction formed and follow the color and of the product, or removal of the colored reactant. And then we can find out the experimental result from there. And then we can also use a conductivity meter and measure the conductivity of the reactant time to time and find out the nature of the carb. And then we can use also measuring changes of masses. This is what we have: cotton plug, wool plug. We have the mixture here, and then we solid reactant in folded paper, and then we can see that we gas coming out from there, and then we change them, note the masses changes. And we can also use this method to determine the rate of reaction and find out other quantitative parameter of rate of reactions. Well, the order of reaction we are talking about, we can do in three ways. One, by plotting a graph against against concentration of reactant, plotting a graph, concentration of reactant against time, deduce successive half-lives from graphs and of concentration against time. Well, by this, we can see that the reaction rate, the concentration, tells us whether a reaction is zero order, first order, second order, or third order. Note that it is very rare that we get higher than second order reaction. So we are talking let us discuss one by one. A zero order reaction, we take the ammonia, and then when we heat it with hot tungsten as catalyst, we get nitrogen gas and hydrogen gas. And the rate reaction is the constant, rate is equal to constant K, and then concentration of ammonia. And then concentration, if we have to power zero there, then it's 1, so K is K. So that rate is equal to K, and this gives a horizontal straight line in the graph. That's what is here. We showed it here, you see, that concentration of reactant, and then reaction rate in mole per cubic decimeter per second. We plot it, and if we get a straight line, we call this this is the zero order reaction, rate of reaction is equal to the rate constant. If we take a first order reaction, for example, this one, we are decomposing nitrogen oxides to nitrogen gas and oxygen gas, and the rate reaction is like this. Usually it is written like this, and this is a first order reaction. And for first order reaction, if we plot the concentration of reactant and rate reactions, and then we see that it is a straight line passing through the origin. And that is what, if we get this, we could say that this reaction is a first order reaction. And rate of reaction is K, rate constant, into concentration of the reactant. Okay, we are going for second order reaction, and in second order reaction, what we see that we take nitrogen dioxide and carbon monoxide and get nitrogen oxides and carbon dioxide. You see, the rate reaction is like this K, the rate constant, nitrogen oxide, the concentration of nitrogen oxide over square. And that what is this is a plot for a curve plot, this red one. If we get a curve like this, we call that reaction is a second order reaction. We have to remember that in case of this second order reaction, rate is directly proportional to the square of concentration of the reactant. So if we take rate at 1 mole per dm cube, then we say K 1 square, it's 1K, and rate 2 mole per dm cube. Per dm cube. Lena. Rate at 2 mole per dm cube, K, 2 square is 4K. So we go to the next slides, and what you see now, figure 1, there's the figure 1, what we are doing, we are plotting the time against concentration of reactant, and if we see that this, then we see that it is, if this is a straight line like this, we call it first order reaction, or zero order reaction, zero order reaction. And then if we get a curve like this, then we call it's a first order reaction. Curve like this, it's a deeper curve like this, we call it second order reaction. That is what, if we plot concentration of reactant against time. Okay, we said also that half-life, we can use half-life. And what is half-life then? It is the time taken for the concentration of a limiting reactant to fall to half of its initial value. Okay, and that figure 2 shows this, that half-life, how we consider. And here is some cyclopropane, and we see the decomposition of cyclopropane and its half-life from that, let's say half-life 4 is the 4 mole per dm cube, and then you see if we got 2 mole per dm cube according as per definition of half-life, then we get this is the half-life for this reaction. And if we go to 2 to 1, we get half-life, then this is the half-life for this. And if we go for 1 to 0.5, we get half-life. 1 to 0.5, half-life is 6.3. So here we can see the half-life is of this reaction is 17 minutes. So here is the graph we plot, time against concentration of cyclopropane. One can also see that if we plot this concentration in time and get a curve like this, this is a zero order, and here, and this is the curve for first order, and this is the curve for second order. Look, here we are talking about half-life, then you see that zero order half-life is decreasing. The half-life is decreasing while the reaction is proceeding. Then for first order, half-life is constant while reaction is proceeding, and then second order, half-life is increasing while proceeding the reaction. That's what is the unique value, and we can identify this by measuring half-life, by measuring concentration versus time, by measuring the other graph we showed in the last slide. Okay, and then we go for an example. What we have to do, we have a balanced reaction. You see, bromate ion and bromide ion in acidic media gives us bromine and water. We know that balanced equation we cannot say about rate, but experimental data by which you can say the initial rate varying with time of different initial reaction, concentration reaction. Using these data, we can calculate. We calculate the constant rate constant of this reaction, rate constant. What we do then, we see from this table, from experiment 1 to 2, what happened? Experiment 1, the bromate ion concentration 0.1 mole per dm cube, and 2, the bromate ion concentration has been doubled. So the initial bromate has a factor of 2, so reaction rate is bromate ion concentration proportional to concentration of bromate ion, is it? And then from experiment 1 and 3, what we are taking, we are talking about bromide ion. It increases 1 and 3, the concentration is 3 times, triple, and the rate is also bromide ion, constant bromide ion. And then if we take the experiment 2 and 4 and take about hydrogen ion concentration, for 2 it's 1 and 4 it's double the rate, increased in the factor of 2, and therefore so rate constant is proportional to hydrogen ion concentration over square of hydrogen ion concentration. So that's what we get from this data. And then if we take the overall reaction, the reaction with respect to bromate ion and bromide ion, it is first order, but with respect to hydrogen ion, it is second order. So we talk that rate reaction is equal to rate constant, concentration bromate ion, concentration bromide ion, and concentration of hydrogen ion concentration. And rearranging this equation, we get rate constant, rate divided by this bromide ion concentrations, this concentration of these ions. And then concentration of these initial rate reaction is given. So initial rate reaction is this rate. This is the reaction. And then we are taking the concentration of all these ions as given in the data. And thereby, if we calculate, we get rate constant is equal to 12.0 dm to the power 9 per mole cube per second. Okay. So this is an example we showed how to calculate the rate, reaction rate constant, etc. And then we go for the next slide and see another problem. What we are doing here, decomposing ethanol to methane and carbon monoxide. This is what is a chemical reaction, and as we may not write this chemical reaction because finding out rate constant, etc. We don't need as I said, we don't need any balanced chemical equation. Okay, so carbon monoxide is second order with respect to ethanol. This is second order with respect to ethanol that is given in our problem value, and where the concentration of ethanol in the gas phase is 0.2 mole per dm cube, the rate reaction is 0.080 mole per dm cube per second. This is what it is given in the problem, and we are asked to find out the rate constant at this temperature, the same temperature, certain temperature. Okay, we have to remember that we have to give the units in the answer, as I said in the earlier stage, that we have to be very careful to present our data with proper unit. Okay, that's what I said. So what the rate reaction is, rate is equal to K, and then the concentration of the, as it is said, is second order reaction, concentration of the ethanol. What is the rate? K, rearranging this, we have rate constant is equal to rate equation and divided by concentration of square of concentration of ethanol. And then this is given, the rate is given, it is 0.080 mole per dm cube per second. And then concentration is also given 0.20 mole per dm cube. So we put this together in the equation and then find out rate constant is equal to 2.0 dm cube per mole per second. Okay, then we go for the next slide and come to our next problems, rate equations and reaction mechanism. What is it? We know very well that reactions occur in a number of steps. That is, specifically when we go for chemical reactions for organic chemistry, we see that these are happening in various steps. We know also other reactions also do happen, do work out in various steps. So these various steps, we call it reaction mechanism. Okay, then these steps do not take place at the same rate. Do you remember? Some could be fast, some could be slow, some could be medium, and this. The overall rate of reaction depends on the slowest steps. The slowest step reaction, we call this the rate determining steps. If the concentration of the reactant appears in the rate equation, then the reactant, a substance that react together to form it, appears in the rate determining step. If a substance does not appear in the overall rate equation, does not take part in rate determining step, we ignore that one. For this, we will see that in propane, this is propane, and we are reacting with iodine, and we will see that the hydrogen ion concentration are involved in the reaction, but not the iodine itself. So that what is a reaction and the proposed mechanism. There are several types, more than one proposed reactions it could be. So the first reaction we can see, this is a very fast reaction which reacts with hydrogen ions, and we get this product. Mind this is a plus ion here, we get this product. And this one becomes slow, and so we get this product and hydrogen ion concentration. Then again, that this is one way, and then next way that we can have this with iodine and fast reaction. So we get this product, and then we decompose this, and that is also a fast product, fast reaction, and then we get this one reaction. This is various proposed mechanism. So what we can conclude here, it is not important to realize that mechanism is not deduced from the kinetic data. This kinetic data simply show us that a proposed reaction mechanism is possible. Well, that much we can discuss in this lecture, and in the next lecture we'll take two more steps, I would say, or two more new issues of reaction kinetics. For example, how the reaction steps are going on, reaction steps, what is stage here, rate of reaction, reaction mechanism, a little bit more, and then also about I would say how catalyst do affect the rate of reaction. That's what we also take in the next lecture. And hopefully the next lecture will be the final lecture on reaction kinetics. Thank you for listening this lecture, and we hope to have the next lecture on ASA level and level chemistry in 2 weeks' times. Thank you very much.